Hello everyone, I'm Hadi Jafarzadeh, and in this course I intend to explain everything related to gas turbine engines or jet engines, from design and manufacturing consideration to maintenance aspects. I highly recommend that those interested in this important field of aviation subscribe to the channel so they don't miss the continuously provided content. Due to the specialized nature of gas turbine, viewer of these videos should have a basic understanding of fluid mechanics and thermodynamics. Therefore, these courses will be suitable for students and graduates in mechanical engineering, aerospace engineering, and even electrical engineering. For this reason, we will use the labels P and even E to indicate the level of the course in the videos. Now, let's take a look at the exciting history of gas turbine engines. In July 1926, A. Griffith published a paper on compressors and turbines, proposing the optimization of axial compressor blades that had been made flat until then and had very low efficiency. His suggestion could significantly improve the performance of axial compressors and turbines. He explained how a jet engine could be constructed by increasing the efficiency of these turbines and compressors. Although he believed this idea was impractical, he stated that it could be used as a turboprop engine. We will become familiar with turboprop engines later in this video. At that time, 6 superchargers were used in internal combustion engines, and they also utilized centrifugal compressors. This paper did not attract much attention. In late 1929, Frank Whittle, a pilot and officer in the Royal Air Force of Britain, designed a turbojet engine by replacing the compressor using Griffith's paper with a centrifugal type. Encouraged by his commanding officer, he sent his idea to the Ministry of Air. He was then invited to meet with one of the officers from the research department, and Griffith himself, who was then a member of the Aeronautical Research Committee. Afterward, Whittle received a letter stating that his simple design could not achieve the desired efficiency for an engine and that current materials could not withstand high temperature, rendering his plan impractical. Whittle became interested in continuing his studies under the Air Force in mechanical sciences and became proficient in mechanical engineering after graduation, while also continuing to pilot. He worked hard to secure funding for building his engine and faced little interest from the Air Force. Meanwhile, Germans had also begun work on jet engines, with the German Ministry of Aviation paying more attention to this matter. Hans von Ohain, a German physicist who was aware of both Griffith's paper and information from Whittle's research, managed to build the world's first jet engine in 1937, named it HE-3B. After World War II, Ohain was brought to America by intelligence forces and participated in jet engine development project in that country. In 1937, Frank Whittle built engine WU, which initially had very low efficiency and was highly unstable due to fuel spread issues, before reaching stable speeds. After modifications, it was tested again in 1938 and managed to operate for 1 hour and 45 minutes, while producing 418 pounds, 2,100 newtons of thrust at 30,000 RPM. Eventually, after years of hardship that caused Whittle illness as well, his engine named W.1 later upgraded to W.2 500 was used in the E.2829 aircraft. O'Hain installed his engine on the Heinkel 178 aircraft in 1939. On the other hand, due to O'Hain's engine low thrust production capability, others like Dr. Franz at Younger worked on building an engine with an axial compressor named Younger Jumo 004. However, due to poor quality steel used in construction, it had a service life of only 10 to 15 hours. This engine was used in the Messerschmitt 262 aircraft, which was the world's first operational jet aircraft. Although this aircraft was deployed late in World War II, it could fly much faster than Allied aircraft at speeds of 900 km per hour and had much more effective firepower. It is reported to have shot down at least 542 Allied aircraft. In one attack by the Allied for bombing missions, it downed 32 out of 36 B-17 bombers made by Boeing. However, operating these aircraft require skilled pilots. If engine 004 accelerated too quickly, its compressor would stall and sometimes explode on startup, so was resulted in the death of 200 German pilots during training. After becoming acquainted with the history of jet engines, we will now examine their main component and type. The overall structure and main components of gas turbine engine include the compressor, combustion chamber, and turbine. Ambient air is drawn in by the compressor where its pressure and temperatures are increased. This air is delivered to the combustion chamber where it is mixed with fuel and burned. As a result, its temperature rises and is used to rotate the turbine. The turbine's rotation is transmitted via a shaft back to the compressor, causing it to rotate, and the cycle repeats. The hot gases are expelled through an exhaust after rotating the turbine. These exhaust gases generate thrust for airplanes. The image shows how a gas turbine jet engine is positioned within an aircraft fuselage. This embedding method is commonly used in supersonic military aircraft. As air passes through an intake duct or air intake, it is delivered to the compressor which sends it into the combustion chamber, and the working cycle of a gas turbine engine continues. The exhaust gases exert force on surrounding air molecules according to Newton's third law. The reaction force is the thrust. In general terms, gas turbine engines can be classified into four categories: turbojet, turbofan, turboprop, turboshaft. There may be other names like ramjet or scramjet that you are familiar with. Although they belong to the family of jet engines, they are not type of gas turbines. Thus, every gas turbine engine is certainly a jet engine, but not every jet engine is a gas turbine engine. The term jet refers to pipe. Therefore, jet engine refers specifically to using fluid flow properties within pipe to produce thrust. In this course, our focus will be on gas turbine engines, as they are more significant than other type of jet engines. In this figure, a turbojet engine is displayed. As shown in the figure, an engine can be divided into two sections, cold section and hot section, where the compressor resides in the cold section while the combustion chamber and turbine are located in the hot section. The term cold does not imply low temperature, but rather indicates temperatures lower than those found in the hot section. The temperature at the compressor's output can reach as high as 1000 Kelvin or 727 degrees Celsius, which is quite high. In contrast, temperatures at entry into the turbine can reach up to 1800 degrees Celsius as regard to metallurgical limitations. We will see later that with increasing inlet temperature into turbines enhances overall engine efficiency. If we mention the basic structure of a turbojet but enlarge its compressor fan blade so that some air passes through what we call its engine core, while some pass around it, this creates a turbofan configuration. Depending on how much air passes around of engine versus through its core, defines two main types of turbofan engines. If only a small amount flows around it, results in low bypass ratio turbofan between 0.3 to 0.6. Bypass ratio is defined as mass flow rate ratio of air passing around of engine versus passing through its core section. In high bypass ratio turbofans, this number can range from 2 up to 15 or even higher, indicating much more airflows around of engine than through its core. For instance, an engine with a bypass ratio of 10 to 1 means for every 1 kg flowing through its core, 10 kg pass around it. In figure 1, we see the F119 engine that is a low bypass ratio turbofan engine and belongs to F-22 Raptor fighter jet, while figure 2 shows CFM56, which is a high bypass ratio turbofan engine, where most incoming air passes around the core. It generates the most of the thrust with this bypassed air. If we place a gearbox at the beginning of a turbojet followed by a propeller that receives the turbine or rotation by gearbox shaft, the results would be developing a turboprop engine. The gearbox prevents propeller tip speed from reaching to supersonic levels, which cause severe vibration and finally propeller destruction. Regarding previous three engines, the hot exhaust gases from their cores, along with cool air exiting their surroundings, play decisive roles in generating thrust. However, for turboprop types, the role played by the hot exhaust gases become less significant. This completely ineffective for turboshaft with all energy extracted from hot gases is aimed solely for driving helicopters, blades, V-shafts, and gearboxes. For turboshaft, turbojet cores are used merely for rotating of compressor, while free turbines rotate blades with extraction of energy from hot gases. A military engine features an afterburner component. The figure represents both turbojet with afterburner as well as turbofan with afterburner designs. Unburned air passing through both inside and outside are burned for increasing exhaust gas amount, leading up thrust increase by at least 30%. However, usage duration for afterburners remain limited only during takeoff or heavy maneuvering, due to increased fuel consumption alongside elevated internal temperature risking damage over prolonged use. This was the first video related to teaching topics concerning gas turbine engines, and we will continue these lessons on our aviation topics channel. If you found this video useful, please don't forget to like it and subscribe for more content. Until next video with further lessons, goodbye and take care.